Good day. Today we are going to talk about linear momentum and collisions. We are going to talk about this problem because there are situations that we cannot yet understand or solve given what we already know. Remember, we have already talked about forces, and then we talked about energy. But there are situations such as the one shown in the picture that cannot be analyzed using all of those force and energy. For example, here, try to imagine you are playing billiard and you shoot the white ball into through a line that passes through the four ball and the one ball. And then you hit the four ball, and then what happened is that only the one ball moved and the four ball still remains stationary even if you hit it with the white ball. So this one, you might expect both balls to move after the white ball hit the violet ball or the four ball because that is what conservation of energy tells you. The initial kinetic energy must equal the final kinetic energy. And how come only the one ball moved? Now, you cannot answer that using energy principles, and you cannot answer that using force principles. So we need another concept, and that concept is the linear momentum. Same here. So a 60-kilogram archer stands at rest on a frictionless ice and fires a 0.03 kilogram arrow horizontally at 85 meters per second. With what velocity does the archer move across the ice after firing the arrow? So because of recoil, after the archer fires the archer will move back, and especially since it is standing in frictionless ice. So how do we solve this problem? We cannot solve this using uh, energy and second law. What we do know is Newton's third law of action and reaction. For every action, there is an equal and opposite reaction. As the force that the bow exerts on the arrow, there is an opposite force wherein the arrow somehow the bow exerts on the archer. And that force is equal and opposite. So that causes the archer to slide back on the ice with the speed that we are looking for. We cannot use kinematic equations for constant acceleration because acceleration is not given. We cannot use force models because we don't know anything about the forces in this equation. We can't use kinetic energy models because it's not given what the elastic potential energy is of the string, diba? So there are many things that we don't know. But that's why we need to learn about momentum. So we do know action and reaction, right? So from the Newton's third law of action and reaction, let us derive the new concept of linear momentum. So say for example, you have an isolated system of two particles, mass 1 and mass 2, as you can see here. As you can see here, mass 1 moves with velocity v1 and mass 2 moves with velocity v2. But mass 1 and mass 2 are also interacting with each other with a force. Let's say this force is the gravitational force. So you have here a force pair, F21 and F12, where F21 is the force that mass 2 exerts on mass 1, and force 12 is the force that mass 1 exerts on mass 2. According to Newton's law of action and reaction, force 12 and force 21 should be equal in magnitude but opposite in direction. In other words, these two vectors are negatives of each other. If you remember your vectors, the negative of a vector is the same magnitude but opposite in direction as the original vector. So if we rewrite that, we get force 1, 2 plus force 2, 1 equals 0. Recall that this is an isolated system, so there are, if we define our system to be both mass 1 and mass 2, we assume now that there are no external forces acting on the system. So from there, we know, like if we look at mass 1, the only force acting on mass 1 is F21. So let me write something. So if we look at mass 1, the only force acting on mass 1 is F21. So if we use second law, summation of forces is equal to mass A. That becomes F21 because there's only one force, which is F21, and M1A. So F21 is M1A. So we can replace F21 with M1A. And we can also replace F12 with M2A. So we get this equation, M1A1, oh yeah, A1, acceleration 1. M1A1 is equal to plus M2A2 is equal to 0. So remember, we are trying to derive momentum. Okay, so we replace acceleration then with the definitions of acceleration, right? Acceleration is the first derivative of velocity with respect to time. So m1 dv1 over dt plus m2 dv2 over dt. Next step is we put mass 1 inside the derivative because we are assuming that mass 1 is constant, and we're also assuming that mass 2 is constant. So, right, so we can now come up with this final equation that the derivative of m1 v1 plus m2 v2 with respect to time is 0. Well, what does that tell us? It tells us that m1 v1 plus m2 v2 is constant, right? Because the derivative of a constant is 0. So this sum m1 v1 plus m2 v2, like the product of the mass of the first particle and its velocity plus the product of mass of the second vector and its velocity, this is a constant. And in particular, d over dt, it's constant over time, which means that over time, if this system remains isolated, the this sum of products remains constant. So even if maybe after some time the velocity v1 changes, velocity 2 will also change accordingly, so that the total mass, the total sum remains constant. This is a conservation situation. So this quantity m1 v1 or mass times velocity is conserved over time. It doesn't change over time so long as the system remains isolated. So the total energy of the isolated system is constant over the time interval, and we can now define, because this is so special, no? That some can be constant over time. We can now define m times v, which is the main product in this constant, mass times velocity. Now we define it to be the linear momentum. No? The linear momentum of a particle or an object that can be modeled as a particle of mass m moving with a velocity v is defined to be the product of the mass and velocity of the particle. The linear momentum p is equal to m times v. And the linear momentum, as you can see, is a vector because it is a product of a scalar quantity m and a vector quantity v. So the direction of momentum is the same as the direction of the velocity, and it has dimensions mass dimension times length over time dimension for velocity. So kilogram times meter per second. So that is the SI unit for momentum. So now, if your velocity is moving in the in 3 dimensions, then you have x components for the velocity, y component for the velocity, and a z component for the velocity. Similarly, you have the x component of the momentum, the y component of the momentum, and the z component of the momentum. So these are the corresponding formulas. The momentum, it provides a quantitative distinction between heavy and light particles moving at the same velocity. So if you have two objects that are moving at the same velocity, but one object is heavier, like a bowling ball versus a baseball. So even if they move at the same velocity, they have different momentums because one object has the heavier mass. In fact, Isaac Newton used to call this the quantity of motion. Momentum used to be known as the quantity of motion. And in my opinion, it's a more descriptive name for what is actually happening, the mass times velocity. Kinetic energy is also, it also involves mass and velocity, right? 1/2 mv squared, right? You remember? So what's the difference between the two? And do we really need another concept that also involves mass and velocity? Well, we do, because the difference between kinetic energy and momentum is that kinetic energy is a scalar quantity and momentum is a vector. So, moreover, kinetic energy can be transformed to other types of energy like potential and internal, but there's only one kind of linear momentum. It's just mass times velocity. Okay. Linear momentum and force. Now, because of our new definition, momentum, mass times velocity, we can actually express the second law, this one. Sum of forces is equal to mass times acceleration in terms of momentum. So what we just need to do is just to call acceleration in terms of dv over dt. And then we put the momentum, the mass inside, right? Assuming that the mass is constant. So now you have the mv, right? So this is the other form of second law, summation of forces acting on an object is equal to the change in momentum, dp over dt of the object. So the time rate of change of the linear momentum of a particle is equal to the net force acting on the particle. The time rate of change, as I mentioned, of the linear momentum of a particle is equal to the net force acting on the particle. Actually, this is how Isaac Newton presented his law. Summation of forces is equal to dp over dt originally. So, right. Let's look at this multiple choice question. Two objects have equal kinetic energy. How do the magnitudes of their momentum compare? So the correct answer is not enough information to tell. So why not? Two identical objects, for example, m1 equals m2, traveling at the same speed v1 equals v2, have the same kinetic energies and the same magnitude of momentum. So if this is the case, k and k1 equals k2, and also p1 momentum is equal to p2 if masses and velocities are the same. However, for particular combinations of masses and velocities, to satisfy k1 equals k2, but not p1 equals p2. So if it's not stated how, if the masses are the same or the velocities are the same, you can come up with various combinations of mass values and velocity values such that the kinetic energies are the same, but the momentum may not be the same. For example, you have a 1 kilogram object mass 1 kilogram, and the velocity is 2 meters per second. This guy has the same kinetic energy as another object whose mass 2 is 4 kilogram, moving at 1 meter per second. So if you calculate the kinetic energy for this guy versus this guy, you get the same kinetic energy, but clearly they have different momentums. 1 times 2 is 2 for the 2 kilogram meter per second, and 4 times 1 is 4. So it is possible that two objects may have equal kinetic energies, but they have different momentums. Your physical education teacher throws a baseball to you at a certain speed and you catch it. The teacher is next going to throw you a medicine ball whose mass is 10 times the mass of the baseball. You are given the following choices. You can have the medicine ball thrown with the same speed, the same momentum, same kinetic energy as the baseball. Rank these choices from easiest to hardest to catch. So, you want the baseball and the medicine ball thrown at the same speed, same momentum, or the same kinetic energy. Let's see what the correct answer is. Correct answer is you want the easiest is for the medicine ball to have the same momentum as the baseball. And the second easiest is that both have the same kinetic energy. The third easiest is both have the same speed. Why? Because slower the ball is, the easier it is to catch. If the momentum of the medicine ball is the same as the momentum of the baseball, the speed of the medicine ball must be 1/10 the speed of the baseball, because the medicine ball has 10 times the mass. If the kinetic energies are the same, the speed of the medicine ball must be 1/√10 the speed of the baseball, because of the squared speed term in the equation for kinetic energy. The medicine ball is hardest to catch when it has the same speed as the baseball, because it is already heavy and you still throw it at the same speed as the baseball. That's very difficult. Now, again, we're going back here for isolated systems. We just right. So this is what we, if you remember, we got this like result earlier. Now, knowing now what we know now about M1V1 and M2V2, that we define MV as the momentum, we can express this equation into this other equation. The derivative of P1 plus P2, momentum 1 plus momentum 2 over time is equal to 0. And that implies that if we call P1 plus P2 as the total momentum, that implies that the total momentum of an isolated system is constant, which means that whatever change there is in the momentum is equal to 0. In the total momentum, the change is equal to 0. And that also means that the initial momentum of the first particle plus the initial momentum of the second particle is equal to the final momentum of the first particle plus the final momentum of the second particle. Okay, because so if initially, for example, if initially the momentum of the first particle is 5 and the momentum of the second particle is 4, making the total momentum 9. Then later on, you discover that the the particle stopped, right? So it has the final momentum of 0. The first particle stopped. So you expect the second particle to have a momentum of 9 to compensate for the fact that the total momentum needs to be constant. That the total momentum before anything happened should be equal to the final momentum after something happened. So, right. So what else, no? The total momentum in X, Y, and Z directions are all independently conserved. So the momentum is conserved along the X, momentum is conserved along the Y, and momentum is conserved along the Z for even just one particular situation. So whenever two or more particles in an isolated system interact, the total momentum of the system does not change. For energy, the system is isolated if there are no transfer of energy across boundary of the system. Remember this? But for momentum, there should be no external forces on the system. So we can only use conservation of momentum if there are no external forces acting on the system. So the total momentum of the isolated system at all times should be equal to the initial momentum. This is true for any type of forces acting on the particles on the system, whether the forces are conservative or not conservative, or whether the forces are constant or varying. The only requirement should be that the forces must be internal to the system and there are no external forces acting on the system. We can use the conservation of linear momentum idea, which is the um, change in total momentum is equal to 0, right? So that's what makes this powerful, right? The concept of momentum is powerful because all you need to know are the masses and the velocities of all the particles. Masses and velocities. You don't need to know what kind of forces are acting internally in this isolated system, right? Don't need to know energies. All you really need are the masses and the velocities. So that makes it really powerful. Helps us solve a lot of problems. So this is what I'm saying, no? So if you have identified your system to be analyzed and you have defined your system boundary and you have there are no external forces acting on the system, we can say that the system is isolated. In that case, the total momentum of the system, which is the vector sum of the momentum of all the members of the system, is conserved. Right. So I really like these forms. I'll write that here. No? Like you have two particles. So the initial momentum of the first particle plus the initial momentum of the second particle. If you add the two, the sum should be equal to the final momentum of the first particle plus the final momentum of the second particle. So, right. This is again true for isolated systems where there are no external forces acting on a system. Okay. So let's just have one example and I'll stop the video. A 60-kilogram archer stands at rest on a frictionless ice and fires a 0.03-kilogram arrow horizontally at 85 meters per second. With what velocity does the archer move across the ice after firing the arrow? The recoil velocity is what they say. So as you shoot the arrow moves forward and the shooter, the archer, moves backward a little bit. With what velocity does it move backward? We can solve this problem with a conservation of momentum. We cannot solve it with models based on motion, force, or energy. But we can easily solve this using momentum. First, we have to define our system. Our system should be consisting of the archer and the arrow. So the system is actually not isolated because the gravitational force and the normal force from the ice act on the system. So this is not isolated because there are external forces acting on the archer, the gravitational force and the normal force. However, these two forces are vertical and perpendicular to the motion of the system. Gravitational force is downward, perpendicular to the motion of the system. Normal force is upward, also perpendicular to the horizontal motion of the system. So there are no external forces in the horizontal direction. No horizontal forces in the horizontal direction. And so we can assume and apply the isolated system model for momentum in terms of momentum components in this direction. So this is given, no? The mass of the first, mass 1, mass of the archer, 60 kilograms, mass 2, mass of the arrow, 0.03 kilograms, and the final velocity of the arrow is 85 meters per second in the I-hat direction. So we know that the total momentum is, the change in momentum is 0. So that means that the final momentum minus the initial momentum is equal to 0, or the final momentum is equal to the initial momentum. Or we can have this equation, m1 vmf plus m2 v2f equals 0. All right. Also, I can look at this way, right? It's like you can say before and after, right? Before and after. So before, the momentum of the, like, the momentum of the archer is 0 because the archer is not moving, right? And that the momentum of the arrow, P2, is also 0. So the total momentum, P1 plus P2, before, like, the archer released the arrow is equal to 0. That's why you have 0 component, 0 here. After the arrow is launched, the momentum of the, like, the man, so P1 final, we don't know what that is. That's what we're about to solve. But we do know that the momentum of the arrow is equal to the mass of the arrow times the final velocity of the arrow, which is given, right? But that's why we know that 0 here before is equal to after P1F plus P2F. So that's how you got this. M1 V1F plus M2 V2F equals 0. And isolating V1F, we get an answer of negative 4.25 centimeters per second. So as the arrow moves 85 meters per second to the right, the archer moves to the left, thus the negative sign, but just a few centimeters. That's because the archer is much heavier than the arrow. So it's a lower velocity. Okay, so that, and there are other problems as well that we can, we'll just discuss in our face-to-face class tomorrow to my students. Thank you.